So for the past few lessons, I believe you've been working with problems with right angle triangles using SOHCAHTOA, sine, cos, tan, trig ratios, or you've been doing problems that are related to non-right angle triangles, obtuse acute, using cosine and sine law. And you're probably wondering, why is this title called unit circle? How is a circle and a triangle related to each other? So let me show you. So here we have a unit circle. It has a radius of 1. So this orange line is the radius with a length of 1. So I'm going to take this red dot and move it along the circumference of the circle counterclockwise. And if you notice, as I keep on moving it, a couple of things are changing. Well, the angle between the two orange lines, the radiuses are changing. And if you notice now, what kind of shape do you see here? Yes, you do see a triangle being shown here. And this triangle is actually connected to this red dot, which is a point on the circumference of the circle. As I keep on getting bigger, as this principal angle gets bigger, which is a term I'll define later on, this red dot, or the x and the y coordinates of this red dot, also changes. So one of the goals for today is to calculate algebraically 3 points at 30 degrees. So this is close to 30 degrees, so 0.86, 0.5, but we don't want to get decimal places. We want to get actually fractions in our answer. That's the goal. We're going to take this and move it to 45. So if I move it to 45-ish, all right, I don't want to get 0.7, 0.72. We're going to actually get the actual exact value, which is a fraction form. And over here, here's 60 degrees, 60 degrees, give or take. We want to figure out this point here, but we don't want to have it in decimal form. So in the next slide, we're going to actually show you how to, well, I'm going to show you how to calculate this. So before we start to calculate those 3 points at 30, 45, and 60, we need to go over a couple of terms. As I mentioned, unit circle has a radius of 1. We talked about that. Quadrants, let's go through the quadrants. So we know that the coordinate system, the Cartesian system, plane, is divided into x and a y. So that's the y and this is the x. So you can see that there's 4 quadrants, four squares in this case. So this one here is quadrant 1. This one here is quadrant 2, 3, and 4. So we do go counterclockwise. Now a couple of things. Initial arm. Initial arm is always 0 degrees, and 0 degrees is going to start always from the center all the way to here, right here. This is called your 0 degrees. I'll put an arrow here. This is called your initial arm of 0 degrees. Now principal angle, this one here, all right? Well, principal angle is the angle between the initial arm and the terminal arm. It actually dictates how far to move. So let's just say the principal angle, we're interested at 30 degrees. So let's just say 30 degrees. I'm going to draw 30 degrees here. So here, this is your principal angle. And this thing I'm drawing here is called the terminal arm. Terminal arm. Okay. And the second thing is standard position. Well, what is it? Well, it's the position of the terminal arm depending on what the principal angle is. So in this case, I drew the standard position of the terminal arm at a principal angle of 30 degrees with a radius of 1. So now let's start to calculate from an algebraic approach the x and the y value of that red dot, depending on what angle that we're going to start off with. So our goal in this is going to focus on 30, 45, and 60. So let's actually start with the 45-degree principal angle. So let's actually take this red dot and move it where the principal angle is 45 degrees. So now, if you notice how we have these 2 shapes involved. We have a triangle, specifically a right angle triangle, embedded in the circle. And this triangle is actually connected to the red dot over here. And our goal for this example is to calculate the specific exact value for that x and the y red point there. And what I mean by exact value, I do not want to have my answer to have a non-repeating decimal form. Meaning, I want my answer to be in a fraction form. So I took the triangle from before and just redrew it over here. So here's my, but I'm going to focus on quadrant 1. So if you notice here, we have a triangle with 45 degrees. It's a right angled triangle. And let's find the third angle. Well, we know that all angles in the triangle are up to 180, so this is going to be 45. Now, this is a triangle where two angles are the same. Now, what type of triangle has angles where two angles are the same? Just two, not three, two of them. It is a isosceles triangle. Isosceles means that these two sides are going to be the same. And the goal, one of the goals is to get the coordinates of x and y. Now, that means from here to here is going to be x, and from here to here is going to be y. And we know that x and y are going to be the same because these two sides are the same. And we know this is a unit circle. That means this piece here, we call it the hypotenuse, is going to be 1. And keep in mind, hypotenuse is always across from the 90 degree in a right angle triangle. So how are you going to solve for x and y? Or in this case, I'm going to call it x and x because they're the same. We're going to be using Pythagorean theorem. A square, b square. So a square, b square is going to be this. These are the two smaller sides. This is going to be the hypotenuse. We're going to add like terms. We're going to divide it by 1/2. Then we're going to divide. So we're going to take the square root, opposite inverse operation of this. That becomes square root of 1/2. The numerator is just a 1. This is just a √2. Now we can rationalize this because we don't want to. Sometimes we not want to have a square root in the denominator. That becomes √2 over √4, and that gives you √2/2. And this is our x. So over here, that means this x here is going to be √2/2, and the y is also √2/2 because x and y are the same. And if you put these two numbers in your calculator, you can take 1 divided by √2, or this √2/2, you could actually end up getting 0.70, pretty much a lot of decimal places with no repeating patterns. So there is an alternative way to solve for x and y. So let's just take the same triangle, 45 principal angle, and solve for x and y. So let's just say you didn't know that this triangle was an isosceles triangle. How would you be able to solve for this? Well, we know that this is a right angled triangle, and this is our reference angle. And going back to trig ratios, the opposite of 45 is y, so that's your opposite, and this is your adjacent. So let's say I wanted to solve for y first. Well, what is y? Y is opposite, and we know that the 1 is the hypotenuse. The hypotenuse is across or opposite of the 90 degree angle. So we're going to be using OH, which is sine angle 45 degrees is equals to opposite over hypotenuse. In this case, it's going to be y/1. And now in this case, sine 45 degrees is equals to y. So how do you evaluate sine 45? So make sure your calculator is in degree mode, and when you type in sine 45 in your calculator, there's a couple of things that you could get. You could get, depending on your calculator, you may get √2/2, which is the exact value, but there are some calculators that don't have that ability, meaning it will give 0.707106. So if you notice, it is a decimal place, but it's a decimal place that doesn't repeat. And if it doesn't repeat, it is kind of difficult to put it into a fraction form directly. And I just said that I do not want my answers to be in non-repeating decimal form. So that's why using the Pythagorean way will give us an answer, which is this number here, and you put that in your calculator, you're going to get exactly this non-repeating decimal irrational number, we call it. So if you're to calculate the x value on your own, it's pretty much the same thing. You'll get the same result, but you're going to be using not sine instead, but cos. I'll leave that for you guys to do on your own. So let's turn our attention to the 30 degrees. So I drew a triangle 30 degrees in quadrant 1. It's not the best, but it'll have to do. So how are we going to solve for x and y? So in this case, we cannot use Pythagorean theorem. We don't have enough information about the sides. But we can use SOHCAHTOA. This is a right angled triangle, where 30 degrees is your reference angle. We do have a side. You have the option, you can actually call this 60 degrees, but we don't really need to. We're gonna just focus on the 30 degrees. So how are you gonna solve for y? Well, you're gonna be using one of the sine or cos or tan. So let's label the sides. This one is going to be the hypotenuse, and 30 degrees and y. The y is actually opposite of the 30 degrees, so this would be the opposite side. and this would be the adjacent. Might as well just label the x. So let's actually figure out y. So let's solve for y using opposite hypotenuse. So that would be sine. So we have sine angle, which is 30 degrees, is equals to y divided by 1. Anything divided by 1 is the same thing, so I'm just going to leave it as y. So what's y equal to? Now when you type this into your calculator, you're going to end up getting 0.5. And 0.5 can actually be put into a fraction form. 1 over 2. Now let's solve for x. Solve for x. Now there's a couple of ways to solve for x given our situation. Now keep in mind, I do not want to have repeating decimal places in my answers. So to do this, all right, let's just say you happen to use trigonometry. So in this case, we have adjacent and hypotenuse. Okay, let's use ka. So we're going to use cosine 30 degrees is equals to x over 1, the same thing as before. The 1 doesn't matter, divided by 1. And if you put this in your calculator, you're going to get 0.866025 equals to x. And it keeps on going. There's no repeating patterns. So at this moment, it's impossible to put this into a rational form, a fraction form, from here to here, given the situation. So how can we solve for x without using trigonometry? Because we do have, I don't want decimal places. Well, let's look at our triangle right now. I'm just going to redraw this triangle. So we have this, 30 degrees. And we know that this piece here is 1 over 2, and this is 1. Well, how do you solve for x? You don't need to use trigonometry. This 30 degrees doesn't really need to be part of the alternative solution to find x. We can actually go back to grade 9 techniques and use Pythagorean theorem. So in this case, you have a squared plus b squared is equals to c squared. You have a square, let's call it x squared plus 1 over 2 squared is equals to 1 squared. You do some math really quickly. I'm going to just cheat a little bit and get it directly. And you take the square root on both sides. You get root 3 over root 4, and that gives you root 3 over 2. And root 3 over 2 is called exact value. It's exact form. It's a fraction form. And if you take root 3 over divided by 2 in your calculator, you're going to get this massive, exact same massive decimal place. So going back to the diagram, so on the circle, we know that the x, which we used over here, x is root 3 over 2, and the y is 1 over 2. So let's draw the 60-degree triangle. So 60 degrees, so here's your 0-degree arm, and then let's actually draw 60 degrees, a lot bigger than 30, so it's going to look something like this, give or take. So that's 60 degrees, the principal angle, and we're going to go straight down. And over here, imagine this is a circle. I'll do the best that I can. It's not the nicest, but it'll have to do. Now, if you look at this right now, these two triangles have something in common. Well, what do you mean? They both have a 90 degrees. This has a 30, but actually I erased something that we didn't have to use, but it's actually 60 degrees. We didn't use that before. Now you do the same thing for here. You figure out this other angle on top. This is 30 degrees. So you notice these triangles have exactly identical angles, and they also have the same radius from here to here, the edge of the circle. So these two triangles are actually identical. What that means is this side here, the shorter side, is actually the same thing as the shorter side of this, which is 1 over 2. Now this one over here is going to be the longer side of here, which is actually root 3 over 2. In other words, this piece here, the xy coordinate of that piece, is the same thing as these two numbers here, but they are switched. They are switched.